So this week we're going to talk about the wrist and hand, and they're in two separate chapters in the book. And I know that's a ton of information, but they're very closely related, and you had some time to work on them in lab, so hopefully it won't be an overwhelming amount of information. So I've also noticed that as the quarter wears on, my lectures start to get longer and longer. I don't know if there's more to say, or I just am less diligent about allowing myself to blab on. So I will try to stay on task in this lecture. The wrist is two major articulations, the radiocarpal joint and the midcarpal joint. The radiocarpal joint, not surprisingly, is the articulation between the radius and the proximal row of carpals. The midcarpal joint is the articulation between the proximal row of carpals and the distal row of carpals. There's also the ulnocarpal space, which is just distal to the ulna. There's an articular disc there for absorbing compressive forces. And it is part of the radiocarpal joint, even though the ulna doesn't really touch the carpals. In terms of terminology, palmar is synonymous with anterior, or the palm of your hand. Dorsal, synonymous with posterior, or the back of your hand. The distal radius and the ulna we talked about in the forearm and elbow chapter. The radius and ulna together form a concavity that articulates with the convex proximal row of carpal bones. The concavity is bordered laterally by the radial styloid process and medial by the ulnar styloid process. So there's a tubercle, which is very palpable. That's the nice thing about the wrist and hand. Just about everything is palpable. Kind of like the feet and ankle. It makes it easy. The radial tubercle is also called the dorsal radial tubercle, or Lister's tubercle. And I'm palpating it right now. It's pretty easy to find. It's a bone projection on the dorsal aspect of the distal radius, and it guides the direction of several of the wrist and thumb extensor muscle tendons. So that's an easily palpable bony landmark. The proximal row of the carpal bones includes the scaphoid, lunate, triquetrum, and pisiform. The pisiform is actually a sesamoid bone that's embedded in the flexor carpi ulnaris tendon. On the bony models, it shows it attached to the triquetrum, but it really isn't. It's floating in that tendon. It increases torque of the flexor carpi ulnaris, like a lot of our sesamoid bones. The distal row includes trapezium, trapezoid, capitate, and hamate. So there are lots of different mnemonics to remember the carpal bones. The one that I had when I was in school was Sally left the party to take Kathy home. That one always sticks in my mind. I remember thinking of it at the when I was taking my board exam. But another one, and there's some of these are listed in the lab manual. Another one that some people like is some lovers try positions that they can't handle. So whatever mnemonic you use, you can make up your own if you want to remember the carpal bones. But those are good things to remember. And we're also going to remember where they are and how to palpate them and who they articulate with. So the bones within the proximal row are loosely joined by strong ligaments. There are strong ligaments that tightly bind the distal row, and that's to provide stability, a rigid base for articulations with the metacarpal bones. So the proximal row is more mobile and the distal row is more stable. The carpal tunnel is partially formed by the transverse carpal ligament bridging the palmar side of the carpal bone. So just like the feet where the bones form a lot of the arch, we have arches in our hands as well. And part of that arch forms the carpal tunnel, which serves as a passageway that helps protect the median nerve and the tendons of the flexor muscles of the digits, the extrinsic flexor muscles. So we'll talk more about the carpal tunnel. A lot more, not just in this class, in other classes too. So the joint structure of the radiocarpal joint, the proximal part consists of the concave surface of the radius and the adjacent articular disc of the ulna. And the distal part consists of the convex articular proximal surfaces of the scaphoid and lunate, mostly, and a little bit of the triquetrum. Approximately 80% of the forces that cross the wrist pass through the scaphoid, lunate, and radius. So the other 20% are distributed through that articular disc in the triquetrum and the ulna. So lots of forces through those three bones. The scaphoid is the most commonly fractured carpal bone, and it's because of where it articulates with the thumb. A lot of times if you're holding onto something like a ski pole and you crash and your hand gets jammed, the scaphoid is the one that takes the brunt of it. The ulnar located carpal bones, the triquetrum and the pisiform, and the distal ulna are less likely to fracture from falls because they're not in the direct path of weight bearing. You have that ulnocarpal space, which is relatively wide space between the distal ulna and the ulnar carpal bones, and it helps buffer the forces that cross the wrist. So the mid-carpal joint separates the proximal row and the distal row of carpal bones. So like a lot of the joints in the foot, it's not a joint between one bone and another bone. It's where lots of bones come together. The most prominent articulation of the mid-carpal joint is formed between the head of the capitate, which is a longer bone, and the socket formed by the distal structures of the scaphoid and the lunate. So a lot of the force is directed through that. The wrist joints are enclosed within a fibrous capsule like most of our joints, and they're thickened by extrinsic and intrinsic ligaments. So just like we talked about extrinsic and intrinsic muscles, extrinsic ligaments have proximal attachments outside the carpal bones but attached distally within the carpal bones. Intrinsic ligaments have both proximal and distal attachments located within carpal bones, and we'll talk about all the individual ones. Not all of them, but the ones that I want you to be highly aware of. So the extrinsic ligaments of the wrist include the dorsal radiocarpal ligament, which limits extremes of flexion. So it's dorsal, it's on the extensor surface, the posterior or dorsal side. It resists extremes of flexion. That makes sense, right? It attaches between the radius and the dorsal side of the carpal bones. It says carpal bone, but we know it's carpal bones. The radial collateral ligament, if it were in another joint, it would be called the lateral collateral ligament, but it's on the radial side, the thumb side. It resists extremes of ulnar deviation. It's strengthened by muscles such as the abductor pollicis longus and the extensor pollicis brevis. So it's not just the ligament that's taking the forces. We get a lot of forces in our wrist, and we have lots of structures to absorb them. So the palmar radiocarpal ligament, just like the dorsal one is on the posterior side, the palmar is on the anterior side. It resists extremes of wrist extension. It's the thickest ligament of the wrist, because probably extremes of wrist extension is more what's happening in real life. That's why it's the thickest ligament. Form follows function, right? Ulnar collateral ligament, which in someplace else in the body might be called the medial collateral, resists extremes of radial deviation. It helps stabilize that distal radio-ulnar joint. And it's part of the ulnocarpal complex. So that articular disc and the other bones. So the ulnar collateral ligament helps stabilize that. The intrinsic ligaments of the wrist as a group, they interconnect various carpal bones. They help transfer forces between the hand and the forearm. And they maintain the natural shapes of the radiocarpal and midcarpal joints, thereby minimizing joint stress during movement. So we're not necessarily going to talk about every little one of those, but just to know as a group they have those functions. In terms of wrist instability, normally the wrist remains stable when it's compressed, even under substantial forces, and that allows us to push things, to push up on our hands, to do planks. Everybody does planks, right? But damage from large forces or typical wear and tear from aging can significantly destabilize the region. So a lot of times for a weak, painful wrist in therapy, we're trying to strengthen, we want to relieve pain, and we want to educate the patient on the ways to protect the wrist. It often includes splinting. So the diagrams from the book, it's kind of a stylized version of how the forces are transmitted and what a compression force can do to the wrist. It's like knocking a train off the tracks. I think that's what they're trying to tell us there. So The osteokinematics of the wrist involve flexion, extension, and ulnar and radial deviation. The wrist does not spin in a circular motion relative to a fixed radius. So it's 2 degrees of freedom, 2 planes of motion. Portions of the radiocarpal joint naturally block the twisting motion. Pronation and supination are not hand or wrist motions, they are motions of the forearm. So it's 2 degrees of freedom, and we can do circumduction because that's the combination of flexion, extension, abduction, or ulnar and radial deviation in the case of the wrist. The wrist movement's axis pierces the capitate head. So you can think of the capitate as being the captain of the wrist. If you want, you don't have to think of it that way. But it's the center point. It's where the 2 axes cross. The medial lateral axis for flexion and extension goes through the capitate, and the anterior posterior axis for radial and ulnar deviation. Rotation of the capitate can direct overall path of the entire hand. So again, it's not rotated within the hand, but it's rotated by the other structures in the arm, like the forearm or the shoulder. Excuse me. So in the sagittal plane, around the medial lateral axis, the radiocarpal joint or the wrist joint can do flexion and extension. From a neutral position, the wrist flexes about 70 to 80 degrees and extends about 60 to 65 degrees. Total flexion normally exceeds extension by about 15 degrees. So if you can flex to 90 degrees, I can do it passively. I can press myself into that. Then you have hyperflexible wrists, which is pretty common actually. Extension is limited by the thicker palmar carpal ligaments and the carpal bones making contact with the dorsal side of the distal radius. So it's a little bit of a firm end feel from the ligaments, and you can get into flexion is more of a hard end feel because it's bone on bone. In the frontal plane around anterior posterior axis, we get radial and ulnar deviation, which are these special wrist names for ab and adduction. On the average from the neutral position, full ulnar deviation is about 30 to 35 degrees, and full radial deviation is less, about 15 to 20 degrees. Maximum ulnar deviation is normally twice that of radial deviation, mostly because of that ulnocarpal space. We have more room on that side. So when we talk about these averages, it's averages over, they take these averages over thousands and thousands of people. So if you are out of the average range, it doesn't mean there's anything wrong. It doesn't mean there's anything pathological. It just means that you're out of the normal range. You're on one end or the other of the bell curve. So unless someone's actually having a problem with it, there's nothing wrong with being out of the normal range, as long as both your sides are the same. So a lot of times using someone's unaffected side as a reference point for what is normal for them is better than using those norms. So that picture with the railroad tracks, we talk about the arthrokinematics of the central wrist column, which is a series of articulations or links between the radius, lunate, capitate, and the third metacarpal bone. So the radiocarpal joint articulates between the radius and the lunate, the midcarpal joint articulates between the lunate and the capitate, and the carpometacarpal joint between the capitate and the third metacarpal is part of that whole kinetic chain. So with wrist extension, you get simultaneous convex on concave rotations at both the radiocarpal and the midcarpal joints. So they're additive. You get some from one and a little more from the next one. The kinematics occur as roll and slide in opposite directions simultaneously at both joints. So full wrist extension elongates the palmar radiocarpal ligament and the palmar capsule and the wrist and finger flexor muscles. And that helps stabilize the wrist in an extended position, which is useful for when you're bearing weight through your upper extremity, because when you're bearing weight through your upper extremity, like in a plank, you're in that full wrist extension. So the arthrokinematics of wrist flexion are similar, but in the reverse, just like we've talked about all along. So ulnar and radial deviation occur through simultaneously convex on concave rotations at both joints as well. So radial deviation at the wrist is limited by the carpal bones going up against the styloid process of the radius, and it's a hard end feel. You can feel it right now.